Assalamualaikum and hi. So we're from Group Copper Aluminium and today we're going to present about copper aluminium alloy. So this is our group members. First, myself, Kamarul and second, Amir Abu Bakar. Third one, Azdreana and fourth, Farhana and last one, Aniqah. So without further ado, alloy is a combination of more than one metal or metal combined with non-metallic elements. These elements are mixed, usually in molten form and solidified to form an alloy with enhanced properties. So in this study, we will focus more on copper aluminium, or I would say aluminium bronze. So this alloy primarily consists of copper and aluminium. The addition of aluminium to copper significantly improves strength, corrosion, resistance, and hardness, and its beneficial properties make COAL alloys suitable for demanding industrial and marine application. So for the physical properties, there are four properties that we could see. First of all, it would be density, with moderate density approximately 7.3 to 7.8 gram per centimeter cube, and is slightly lighter than pure copper. And the second one, electrical conductivity, which is lower than pure copper. The third one would be melting point, around 1025 degrees Celsius, and last, thermal conductivity, where it able to transfer heat but less efficient than copper. Next would be mechanical properties, where COAL has great hardness when it increased with aluminum content, good ductility when the aluminum content is low. It also wear resistant to it also excellent resistant to wear and friction. And last but not least, corrosion resistance. So now, phase diagram. The copper aluminum phase diagram shows how the alloy changes with temperature and composition. At high temperature, it is fully liquid. As it cools, solid phases form depending on the copper to aluminum ratio. On the aluminum-rich side, hard intermetallic compound like theta and mu appear. On the copper-rich side, the alpha phase forms, a solid solution of aluminum in copper that ductile and corrosion resistant. A key for transformation is the eutectoid reaction at 548 degrees Celsius, where the beta phase breaks into alpha and gamma 2. This happens at constant and creates a fine, strong microstructure. The diagram also includes eutectic and peritectic reaction, which form solid phases from liquid and solid mixture. In short, the copper aluminum phase diagram helps to predict phase changes and guide heat treatment to control the alloy properties. Now let's look more closely at the reaction that occur in copper aluminum system. We begin with isothermal reaction, which involves several heat treatment steps. First, homogenization, where the alloy is heated to create a uniform distribution of atoms. Then comes quenching, where the alloy is rapidly cooled to room temperature. This trap aluminium atoms inside the copper matrix, forming a supersaturated solid solution. Next is etching, where the alloy is reheated to a lower temperature and held for a controlled time. During this stage, precipitation happens, which is fine intermetallic compound like copper aluminium 2 begin to form. This particle block dislocation movement and increase hardness through precipitation hardening. Next is intermetallic reaction, where copper aluminium forms stable compounds such as copper aluminium 2. This intermetallic appear during aging and contribute to strengthening. At first, they are small and well dispersed, but with too much aging, they grow larger, reducing strength and making the alloy more brittle. Several factors that contribute to intermetallic compound behave. First, alloying element like ferrum, manganese, and nickel can promote or suppress certain intermetallics. Next, temperature that control how fast atoms move, which too high and particular may, if too high, and particular may caution or transform. Last, time affects the size and distribution, which too short or hardening is incomplete. Too long, if it's too long, the overaging might reduce strength. Last but not next, the solid solution reaction. Solid solution reaction occur in two stages. First is during heating, and second one during. So, for copper aluminium alloys, a solid solution forms when aluminium atom dissolve in the copper. This process happens in two stages, heating and quenching, and is key to strengthening the alloy. During the heating stage, the alloy is raised to a high temperature within the alpha phase region of the copper aluminium phase diagram. At this point, aluminium atoms begin to substitute copper atoms inside the FCC crystal structure. Over time, a stable equilibrium solid solution forms called the alpha phase, where the atoms are evenly distributed. This structure is thermodynamically stable as long as the temperature is maintained. Next comes the quenching stage. The alloy is rapidly cooled. usually in water, to room temperature. This sudden cooling freezes the aluminum atoms in place before they can diffuse out of the copper lattice. They result in a supersaturated alpha phase, meaning more aluminum atoms are trapped in the structure that it would normally hold at low temperature. This phase is metastable, but is critical for further strengthening. This supersaturated solid solution sets the stage for precipitation during aging, where fine intermetallic particles begin to form. These particles hinder dislocation, movement, and increase hardness, a process known as precipitation hardening. So, by controlling the heating and quenching process, we can manipulate the microstructure and mechanical properties of the copper aluminum alloy.
I'm going to talk about the effects of the cuprum alloy material. The first effect is increase the strength and hardness due to solid solution strengthening. The second one is resist corrosion in marine and industrial environments better. The third one, control cooling can produce finer grains and increase strength. And the last one is reduce ductility. Alloys becomes more brittle when intermetallic phase dominate. For the application, we can use this material for marine industry as a seawater fitting because have excellent corrosion resistance. And then for aerospace industry, like our aircraft engine parts because have a good balance of strength. And then for electrical and instrumentation, connected terminals because have a good thermal conductivity. And then for mechanical components, for example bearings, because high wear resistant and low friction. Now, I'm going to talk about the eutectic in cuprum aluminium alloy. So for the composition, eutectic point is at cuprum 11.8% aluminium, means 88.2% copper and 11.8% aluminium. Liquid freeze all at once into a fine mixture of two solids, and it gives the metal a very fine layered structure. We call it as lamellar. And then this process happens at 548 degrees Celsius. The entire liquid alloy turns directly into two solid phase at the same time. And then this is the phase, liquid to alpha plus theta. For transformation alloy, above 548 degrees Celsius, alloy is liquid from copper and aluminium completely melted and mixed. Cool at 548 degrees Celsius, and the reaction happen. They form together. So means this alpha and this theta form together. For the alpha phase, it is soft, ductile and solid solution, FCC. For theta phase, hard, brittle, intermetallic compound. What is the method to improve alloy properties? The first method is grain refinement. The second one is directional solidification. Third one, heat treatment. And then the fourth one is rapid solidification. But the best method is grain refinement because we can increase the strength. And then the eutectic cuprum alloy solidifies at a fixed temperature of 540 degrees Celsius, forming a fine lamellar structure of alpha and theta phase. This unit's microstructure results in a balanced combination of strength, hardness, and customizability. Since the alloy contains no primary phase, the phase composition remains stable below the eutectic point, making it ideal for application that require consistent mechanical properties and good wear resistance. Now, this is the phase diagram, and here is the eutectic point in this orange circle. The eutectic point in the cuprum aluminum system at 11.8% alloy and 548 degrees Celsius is the lowest temperature where the alloy remains fully liquid. Below this point, it solidifies directly into two solid phase. This transformation happens quickly and uniformly, forming a fine lamellar microstructure. The result is a strong, wear-resistant alloy with a good casting properties, making it suitable for application like automotive and marine components. And then this is the cooling curve. Here is the temperature 548 degrees Celsius, and here is the eutectic point start. In the cooling phase above 548 degrees Celsius, the eutectic remains fully in the liquid state. As it cools down, the temperature decreases smoothly over time. During this stage, no phase transformation occurs yet. The process involves only a sensible heat loss, meaning the temperature drops without any solidification taking place. And then during this transformation, the temperature remains constant, forming a horizontal line on the cooling curve due to the release of latent heat of fusions. Once solidification is complete and the alloy is fully solid, the temperature continues to decrease as the solid metal cools further. The last one is about the microstructure for eutectic. This is the microstructure before, and this is after. This is how the microstructure will look like after the eutectic process. And this will result the lamellar microstructure. That's all about eutectic.
So I'm going to talk about hyper eutectic copper aluminum alloy, and where copper aluminum alloy that contain more copper than eutectic composition, which is above 33%, forming hard and brittle intermetallic compound like CuAl2 along with the other solid phases. So the composition where hyper-eutectic copper aluminum alloy has more copper content. A common hyper-eutectic composition is typically in the range of 35 to 50% of copper. This alloy solidify with the formation of primary theta phase, followed by a eutectic reaction forming alpha plus theta mixture. Small addition of elements such as ferrum, manganese, and or nickel are often used to refine the microstructure, improve mechanical properties, and enhance the corrosion resistance. Method to improve alloy properties. First one would be heat treatment. The second one, grain refinement. Third one, rapid solidification, and last one, alloying addition. And the transformation of alloy, where solidification process same as hypothetic, which occur from liquid to solid phase, and composition of alloy has more percentage of copper than eutectic composition. The solidification starts when temperature decreases. The liquid alloy contains a higher aluminum percentage than the eutectic, creates the primary theta of primary solid phase. When alloy cool, it contains copper solidified first. After that, the temperature keeps decreasing until it reaches eutectic region. The eutectic phase formed by lamella involve the structure of solid solution and eutectic compound. The temperature continues to decrease, transform the liquid to alpha theta phase. Hyper-eutectic transformation process continue until it's fully solidified and produce eutectic lamella structure. So I'm gonna proceed with the cooling curve for hyper-eutectic. As a hyper-eutectic copper aluminum alloy with I would say 48% of copper cools from a molten state. The solidification process begins with the formation of primary theta phase, which is CuAl2. This phase starts to crystallize from the liquid before reaching the eutectic temperature, and the onset of this transformation appears as a change in slope on the cooling curve. As the temperature continues to drop and reach the eutectic temperature, which is 548 degrees Celsius, the remaining liquid undergoes a eutectic reaction, forming a fine mixture of alpha and theta phase. This eutectic transformation is represented by a horizontal plateau on the cooling curve, indicating that latent heat is released while both alpha and theta phases form simultaneously. After complete solidification, the curve resumes a steady decline as the alloy cools to room temperature. And now, for the microstructure of CuAl alloy, which is consists of primary theta phase, CuAl2 crystal, which form first during solidification. These appear as dark, blocky, needle-like structure under the microscope. Surrounding the primary theta phase is a fine structure composed of alpha phase and theta phase. The alpha phase provides some toughness, while the theta phase contributes significantly to the hardness and strength of the alloy. However, as the copper content increases, the amount of theta phase also increases, leading a harder but more brittle alloy. This dual phase structure play a crucial role in determining the alloy mechanical properties such as wear resistance, strength, and fracture behavior. So as you can see, for the T1, it's approximate almost all liquid, and for the T2, uh, primary theta form also include with liquid, and for T3, which is point 3, where uh, primary theta form with lamellar structure, and for the point 4, where dark uh, dark line for alpha and theta for the white one.
Assalamualaikum warahmatullahi wabarakatuh. My name is Azdreana Binti so today I will be presenting about hypoeutectic aluminum copper alloy. So what it is? It is an alloy whose copper content is less than the eutectic composition. So what is its composition? The composition that consists 20% of copper and 80% of aluminum. So the position in the phase diagram lies before the eutectic composition, around before the 33% copper that it forms primary alpha phase during solidification. So how do we improve this alloy? First treatment we can use is heat treatment, where solution treatment plus aging treatment that will increase the hardness and strength. Second, grain refinement, where we add small amount of few elements to produce fine and uniform grains. Third, alloying addition, where we add few elements to have few reaction. And fourth is rapid solidification or control cooling, where we know the faster cooling rate lead to finding microstructure. And how do this alloy forms? So it forms that with the solidification process from hypoeutectic aluminium copper alloy begin from the liquid phase as the temperature decreases. Since this alloy has less copper than eutectic composition, it is considered hypoeutectic. The primary alpha phase form first. As the temperature continues to drop, primary alpha dendrites solidify out of the liquid. The remaining liquid become richer in copper until it reaches the eutectic temperature. At 548 degrees Celsius, an isothermal eutectic reaction occurs. This forms a laminar eutectic microstructure between the dendrites. The amount of eutectic depends on the alloy composition and cooling reaction. When fully solidified, the microstructure consists of primary alpha phase dendrites surrounded by alpha plus theta eutectic. The alpha appear light grey or white, and theta phase may appear dark or black under microscope. And then we go to cooling curve of hypoeutectic. As you can see the drawing I have provided for your reference, the temperature drop over time as the molten hypoeutectic aluminum copper solidify. As it begins to cool from liquid state, the first phase to form is the primary alpha solid solution. Since the alloy has less copper than the eutectic composition, this formation causes a slope change on the cooling curve, indicating that the start of solidification. As the cooling continues, more alpha phase forms and the remaining liquid become richer in copper. When the temperature reaches the eutectic point, the remaining liquid undergo eutectic reaction, producing a fine mixture of alpha plus theta phases. In this reaction, appears as a horizontal plateau on the cooling curve, showing a constant temperature during the transformation. After all the liquid solidified into the final microstructure of alpha dendrites and eutectic alpha plus theta, the temperature continues to decrease steadily as the fully solid alloy cools. And then we go to microstructure of hypoeutectic. So this is the draw I will do for you. As you can see, at temperature 1, which is above liquid temperature, the alloy is fully liquid. No solid phase has formed yet. The atoms are in a random motion, and the microstructure is completely homogeneous in the molten state. And then at second temperature, where the start of solidification, just below the liquid temperature, as the temperature drops below the liquid line, primary alpha phase begin to nucleate and grow. Dendritic grains of alpha start forming within the liquid, appear as light structures in metallographic image. The surrounding liquid become progressively rich in copper. At temperature 3, during solidification, between line liquid and eutectic temperature, more alpha dendrites grow as the temperature decreases. The microstructure now consists of solid alpha dendrites embedded in a copper-enriched liquid matrix. No eutectic has formed yet, but the liquid is approaching to eutectic composition. And lastly, at temperature 4, which is at eutectic temperature, the remaining liquid undergoes eutectic reaction, forming a fine laminar eutectic structure between alpha dendrites. The final microstructure consists of primary alpha phase grain surrounded by a matrix of eutectic alpha plus theta.
My name is Sarah and I'll be presenting about the copper aluminium alloy with grain refinement, titanium and boron addition. Grain refinement is the process of reducing the size of crystal grain in the copper aluminium alloy to enhance their mechanical properties. This means that the smaller grains will lead to increased strength, toughness and wear resistance. The first one is the addition for the titanium. The titanium will include the formation of the titanium carbide. And this titanium carbide will form particles that will act as a nucleation site during the solidification, and this will prevent the growth of large grains and promote a finer microstructure. For their strengthening mechanism, according to the half-patch relationship, finer grains will lead to an increase in the material yield strength, making the alloy more resistant to deformation. The second one is boron. Boron will include the formation of borides, which boron will form boride compound, which aid in controlling the grain size during solidification, ensuring a more uniform structure. This addition will enhance its toughness, which will produce a smaller and well-distributed grain that enhance the material toughness, making it more resistant to crack propagation. The next is for the mechanism of grain refinement. The first one is the solidification process. During cooling, titanium and boron will act as nucleating agents, which promoting the formation of fine grains, and this process will stabilize the solidification process and minimize the formation of coarse and weak grains. The second one is stable nucleation. Titanium and boron particles will create a stable nucleation site, which lead to the growth of small, evenly distributed grains and improving the alloy overall strength and toughness. The benefits of grain refinements include three, which is increased strength, improved toughness, and enhance the wear resistance. This will increase strength because smaller grains provide higher yield strength due to the grain boundary strengthening effect according to the Hall-Patch equation. The grain refinement will improve the toughness is because the finer grain structures will have energy absorption, improving the alloy's ability to withstand impact and preventing fractures. Number 3 is the grain refinement will also enhance the wear resistance. This is because alloy with finer grains show lower rate under stress, making them more durable and long-lasting in mechanical application. Next, this is the microstructure of the copper aluminum alloy after the addition of the titanium. Next is the industrial application. The first one, it is being used in the aerospace industry, which aircraft component that need a strong and lightweight material for structural integrity. And the second one is in the automotive industry, which components such as the brake pads and the engine parts which require high strength and wear resistance. The third one is also been used in the electronic industry, which applies in connectors and conductors in electric circuits, where both electrical conductivity and material strength are essentials. The summary of this presentation is that the addition of titanium and boron to aluminum copper alloys leads to the grain refinement, which significantly enhance the alloy mechanical properties, and this process makes the aluminum copper alloy more suitable for applications in the industries which require high performance in terms of strength, toughness, and also wear resistance. That's all from me. Thank you.
Assalamualaikum. Hi, my name is Amirul Abu Bakar. So today I will be explaining how copper aluminum alloys are improved through solution treatment and aging process. So what is heat treatment? Basically, heat treatment is a process used to modify an alloy's microstructure and improve its properties. For copper aluminum alloys, it involves two main steps, which is solution treatment, where the alloy is homogenized, and aging, where precipitates form. Together, these steps increases the hardness, strength, and wear resistance. Heat-treated copper aluminum alloys typically contain between 5% to 11% aluminum. This composition range lies close to the eutectite point and produces a solid solution of aluminum in copper, known as the alpha phase. Upon aging, a second phase called CuAl2 precipitates, contributing to strength through precipitation hardening. This is the phase diagram of the copper aluminum system. You can see the alpha phase region on the left side and the theta phase or copper Al2 forming on the right side. You have the eutectic point at about 11.8% copper and 548 degrees Celsius, where alpha transforms into alpha plus theta. The solvers line, which runs horizontally at the temperature that marks the upper limit of alpha phase stability. In solution treatment, the research I got used in the 5% to 6% copper region to fully dissolve secondary phase before quenching. After heating, the alloy is quenched quickly, causing the temperature to drop rapidly. Then, during aging, the temperature is held in a lower range where precipitates form, causing a plateau on the curve due to latent heat. Finally, the alloy cools to room temperature, locking in new microstructures. The first step is solution treatment. It involves heating the alloy to around 750 to 850 degrees Celsius. At this temperature, aluminum atoms dissolve into copper matrix, forming a uniform alpha phase solid solution. This is followed by a rapid quenching, which traps the dissolved atoms in place, forming a supersaturated solution. And next is aging, where the alloy is reheated to around 150 to 350 degrees Celsius. This temperature allows copper aluminum 2 precipitates to form slowly and evenly throughout the matrix. These particles block dislocation motion, making the alloy stronger and harder. Here's how the microstructure changes. Before aging, the alloy is mostly uniform alpha phase. After aging, you can see fine needle-like or dotted shape structures, which is copper aluminum precipitates dispersed in the matrix. These precipitates are responsible for the mechanical strengthening. As a result, the hardness can increase from around 100 to 180 Vickers, and yield strength also improves. There may be a slight trade-off with ductility, but the overall strength and wear resistance are greatly enhanced due to both precipitation hardening and lattice distortion. To sum up, solution plus aging transformed a basic copper aluminum alloy into a high-performance material. It becomes harder and stronger, with properties suitable for marine components and aerospace parts, and other demanding applications. The key mechanism here is precipitation hardening from copper aluminum particles. That is all from our group. Thank you.